So I'm going to follow pretty much the same format that we did yesterday. Essentially, what we're going to do is how to find confidence intervals for the difference between two proportions. So big long list, but that's essentially what Tensei is about. When can you find these differences? And then how do you find these differences? And is there anything you can interpret from them once you've done that? Now, we already kind of know a little bit about confidence intervals from last time. There are typically three main ones. The three main confidence intervals are the 90% confidence interval. There's a 95% confidence interval. And there is a 99% confidence interval. They are the standard ones that you'll see in research papers and in surveys and polls and whatever else that might use confidence intervals. Although occasionally you might get a homework question that asks for a 98 or a 97 or something, or a 68. I think I've seen that one as well. And we'll show you how to do this process in two ways. I'm going to start by doing it by hand. A couple of reasons, like yesterday, why I want to do that. I want you to understand how the process works so that when you use salt, you're just saving time. It's not like you don't know what to do, you just don't want to do it because it takes too much time, you know, hitting all the buttons and, you know, whatever. Might as well just let the software do it, right? But we want you to understand how to do it. And secondly, sometimes you do get questions where the salt button is not there, so you can't use the salt button. They may just ask you to find the standard error, for instance, and you need to know how to do that separate, right? And so you will need to know how to do pieces of it anyway by hand. So we might as well show you the whole thing. Now, here's one of the very interesting things about this. Is that if you want to find a 90 or a 95 or a 99, the formula for it looks very like yesterday's. But we are interested in the difference between two proportions. So you're going to have one group over here, and that might be, say, Americans, and you get another population over here, and that's Scots. And you want to compare, let's say, how much they drink, right? Is it true that Scots people drink more than Americans, right? Maybe that's what you're interested in, because, I don't know, you're writing a little article in a newspaper or doing a story about it, or you could even be writing a book, who knows? But you want to see what is the difference between the two, if there is one. So, although this is a population, you get a sample, and let's say that sample is 200 American adults, a nice random sample. And you find out that 51 of them out of 200 got drunk once in the last week. So that's how you're going to decide who drinks. Did you get drunk this week? And 51 out of 200 said, yeah, I was drunk on Tuesday. I was drunk, whatever. Now, you went over to Scotland and you notice that you asked a different number, and that's okay. A lot of people think that these two should be the same. It's nice if they are, but they don't need to be. And the proportion of them, that 400 that said they were drunk, 129 of them said they were drunk. And we are going to use this set of data to find a confidence interval for the difference between them, right? So if you took this guy and you subtracted that guy, what would the difference be? Now back to this formula. It's P1 take away P2. That makes sense, right? You're looking for a difference. Plus or minus 1.645 times what's called the standard error of P1 take away P2. The 95% has only one change. And the 99 So do you see that the formula for calculating confidence intervals uses the same statistics, right? The same numbers that you get from the sample. That's what we call a statistic, with a different multiplication factor. When it's 90%, you use this magic number. When it's 95, you use that. And when it's 99, you use that. Okay, so we have got 3 here. Which one of those 3 do you want us to use? Which one? Doesn't matter. It's really just a choice. I didn't catch the end of that. You say it again, please. Oh, lost it. Okay, someone else then. I heard the 9, but I couldn't hear if it was 90, 95, or 99. Okay, Nathan, tell me what to get.
Wait, what?
Which one of those do you want? A 90, a 95, or a 99? Which one of those 3 do you want me to calculate?
Oh, how about a 99?
Okay. So we are going for the most accurate confidence interval, because when you get a 99% one, that essentially means that you are 99% sure that the real answer to the difference will be in that interval, right? 99% sure is not perfect, but nothing is, but it's darn close. So since we're going to use that one, we have a number of things we need to calculate. We need to calculate the difference, which wouldn't be too difficult. And then we have to calculate this guy called the standard error. So let's get this one done. Now, P1 is 51 out of 200. Take away P2, which is 129 out of 400. And that's really what calculators are for. And I'm going to pretend that this question is to 3 decimal places, because we're not going to get exact values out of these calculations. Right. Now there's a remarkable thing. Okay. 06, I don't know. I'll keep it to 4 for lower. Do you notice that the answer is negative? See that? Negative. Now what that's telling me is that isn't P2 bigger than P1? If you take a small number and subtract a bigger one from it, you get a negative answer. And isn't that already pushing towards the Scottish people drink more than Americans? Because this is bigger than that, and a small thing take away a big thing gives you a negative answer. So I put a little bubble around that because I forget where things are. That is this statistic, and now the standard error. And the standard error has 2 formula. This is the one we're going to use. Do you recognize that formula? Isn't that the standard error for a single proportion? So all you do is you add that guy. Are we comfortable with that formula? It's really just an expansion of one that you've got. Now, I said there's two formula, and there is. And the second formula pulls the data, and it uses a p hat pulled, and it's a square root of p hat pulled 1 minus p hat times 1 over n1 plus 1 over n2. Really ugly formula. I choose not to use that formula. And I'm assuming that neither did this textbook. But I want you to be aware that if you did see a question and it said, we pulled the data, then you're going to have to go into the book and find that formula I told you and calculate the standard error using it. And the reason I choose not to use it is, for you to do what's called pulling the data, you have to make a very big assumption about the two different populations. You have to make the assumption that they are roughly, they are equivalent in the sense that they behave the same way, that they've both got the same standard deviations and they're both roughly about the same size and distribution. It's a bit like you could pull the data if you had two groups, males and females, and you were only interested in the percentage that had blonde hair. Could you imagine that blonde-haired women or blonde-haired men? Yeah, there's probably very similar shapes to the data, right? Because although they're men and women, they're probably going to be okay. You shouldn't use it when you're talking about two distinct populations that have nothing in common. What was the analogy I gave once? Suppose you were interested in the drinking habits of French people and German people, and you decided to pull the data because you thought, French and German, what's the difference? They all drink. There won't be much difference between the two. And then you find out that Frenchmen drink wine and Germans drink beer. Can you see how different those two groups are? And if you pull the data when you shouldn't, it distorts it. So after that nice big long speech, I don't like pulled data. I don't do pulled data unless there's a very good reason for it. And you won't need to worry about it because I've tried to avoid you ever needing to use that formula. So back to this ugly guy. It's going to be P1, this guy over N1, P2, this guy over N2. If I leave these damn things as fractions, it's just going to make this calculation even worse. So I'm just going to go back up here and turn them into decimals. So this guy is going to be 0.255, and this guy is going to be 0.3225. I just find it easier to use decimals on a calculator. So here goes. P1 is this fella. So it's a square root of 0.255 times 1 take away that. So that's 0.745, all divided by 200. So that's that bit, plus the P2 one, which is this fella, 0.3225 times 0.6775, all divided by 400. And this is equal to 0.03, I'll round off now. Just for completeness sake, I'm going to put this calculation in, because you may come back and say, I didn't quite remember what you did there. Okay, so this is the information about the Americans, all the ones with ones in it. And this is going to be this information with the Scots people in it. And here's the standard error. Can you already see why using salt, which I'm going to show you, is going to be a lot quicker, right? Because there's a lot of buttons to press and things you have to be careful about. But we now know this number, which is that guy, and we know this number, the standard error. So the 99% confidence interval, which is the difference between the two, plus or minus 2.58 times the standard error of the difference. This guy is a negative 0.0675 plus or minus 2.58 times 0.039. And I'm going to just multiply these two together. So it's going to be 2.58 times 0.039. And that's going to be a remarkably nice answer. Give or take 0.1006. Very nice looking answer. So you take this number and subtract that, you take this number and you add that. So when you subtract them, you get negative 0.1. Check that. Okay. I was going to do that in my head, but I'm not very comfortable about doing that. So here goes. Negative 0.0675 take away 0.1006. And the answer I got here is negative 0.1681. And if I take this and I add that number, so negative 0.0675 add 0.1006, I get at the other side 0.0331. That would be our 99% confidence interval. If I turn it into percentages, it's negative 16.81% all the way up to positive 3.31%. So that is how you find a confidence interval from scratch, right?
Can we have a negative percent?
Yes, now you can. You cannot get it if it's a single proportion. See, if you just ask one group, how many of you got drunk last week? The answer is always going to be positive. So when it's a single proportion, you can only get answers from 0 to 100%, right? 0 to 1. But when it's the difference between two, negatives can happen.
Okay.
And they're actually telling you something. Aren't they telling you that the second guy is bigger than the first guy? So it's not, well, I wonder what that means, right? It's pretty obvious what it means. Now, there are going to be, once you've found your 99% confidence interval, there's going to be a phrase, I think the textbook calls it something like contains 0. And you might think, what is the contains 0? Why is that so important? Well, there are 3 major types of confidence intervals of differences. I'm going to use percentages, and I'm going to use really nice numbers. You could get a confidence interval where everybody is negative, right? So it's the difference is somewhere between negative 5% and negative 2%, right? That's the first situation. You could get a situation where everybody is positive, right? The difference is somewhere between 3 and 11%. Here, the difference is somewhere between negative 5 and negative 2. And you could get an interval, this middle one, that contains the number 0. Now, why do they even distinguish this? once you've found this confidence interval, it would be nice if you could, at least sometimes, use it to prove something is true. Now, if the difference between the two is always negative, what that means is that P1 take away P2 is negative, right? But another way of looking at that is, isn't that another way of just saying that P1 is less than P2? So if we had got it in our Scottish story, wouldn't that means Americans drink less than Scots? Because one is American, two is Scotland. Now, if everybody is positive, what you're saying here is that the difference between the two is guaranteed to be a positive number, right? Great. What's that phrase? Third time lucky? We're done. So when you've completed calculating a confidence interval, you may get a question towards the end that says, you know, one of those 4 choice things. Is there evidence to prove that Americans drink more than Scots, less than Scots? You can't tell the difference, you know, choices like that. And you'll base it based on if everybody is negative or everybody is positive, or if it has what they call contain 0. Now, before we show you SALT, which is where I'm going next, for that question, the one we've just finished doing about the Scotsman and Americans and their drinking habits, would you agree that in this particular question, there's not any evidence to prove that Scots drink more or less than the Americans, and the reason is that this interval contains 0. Now you might say, but look, that's really big and negative, and that's not that big and positive. Can't we use that as evidence? No, the reason we can't is that all the confidence interval does is it gives you a range of values, and the true answer is one of those numbers inside that interval. It could be the 3% number. It could be the negative 16% number, but it's just as likely to be the 3 as it is to be any other number. And because you don't know, because it's any of them, you can't really make any judgment calls. On the other hand, if everybody is positive, it really doesn't matter which one you pick, want to be positive, and therefore it's guaranteed to prove something. And another little part is that they don't spend a lot of time on this, but they should, that you can't do confidence intervals for differences unless you've got a couple of things set up. The first thing is size, sample. Your sample should be big enough for you to do this. You wouldn't do this experiment by asking 2 Americans and 3 Scotsmen. Would you agree that those numbers are so tiny, you couldn't really be sure that anything was true, right? So how does that work? Well, it's N1 P1 has to be greater than 10, N1 minus P1 hat also has to be greater than 10, and at the same time, that's true. Essentially, what this means is that the people who say yes and the people who said no, there has to be at least 10 people in each group. So if you're 500 people something and 82 said yes, and therefore that means the rest of them said no, that's totally fine. But if only 8 people said yes, even if 992 said no, that's not fine. Do not use confidence intervals to do anything. It's not a good idea. In no particular order, the second thing is that the sample should be a, putting the word fair, and representative of population. Right, if I wanted to find out about adults in America drinking and Scotsmen in America drinking. 200 random samples, good idea. Going to 5 pubs and talking to the people in those pubs is not a good idea, because they are not a fair representation of the entire population, right? They're already in a pub, so they probably drink more than typical, right? So you have to make sure that your sample is fair. And that's why we almost always do simple random samples. And the third one is independent populations. The two groups have to share nothing in common. They have to be quite independent of each other. Suppose I collected data on husbands and wives, and I made P1 the husbands and P2 the wives. If I asked any question about politics or about how many times they go out to eat or any question, can you see that those two populations, because they're from married couples, won't they be connected in some way? Because whatever one person says, there's a very good chance that the politics of the other person are similar. Not saying that's the case every time, but enough to distort your data. So don't use population that are connected in some way, because they tend to generate biased data, and you don't want biased data. They don't spend a lot of time on these kind of questions, but I think it's worth mentioning. So a quick pause. Is there anything that I've talked about so far you'd like me to go into more detail? Are we good?
I had a question real quick.
Go for it.
Is a negative 0.0675, is that the margin error, or is that the p hat 1 minus p hat 2?
Oh, let's go. This number here?
No, the one from the before that.
This number here?
Yeah.
Okay. This number here is P1 hat take away P2 hat. That's a statistic for the typical difference between the two groups. Now, do you see this guy here, which is going to be positive? The way it's calculated, it's always positive. This also has a name. This is called the margin of error.
Oh, okay. Got it.
Okay. Any other questions?
No, that's the only question I had. Just wanted to make sure real quick.
No problem. Are we good, guys? Moving on to show you what it looks like when you do it now as homework. Okay. I'm assuming that's a good sign. Have to wait a few moments. Where the heck are we? I think we're here. We are. Okay. So what I'm going to do now is look at some homework questions and how WebAssign kind of does things. Okay. Right. Are you all looking at question 1 WebAssign? So you're not seeing question 1 WebAssign. Are you seeing it? I don't know what I'm saying. What are you saying now?
We see it now.
You are saying in each situation explain. Is that the sense?
Yes.
Yeah.
Oh, good. Okay. So these are just the intro questions. There's what, 12 questions in this section altogether. Let's see what we have. In each of these situations, explain whether the method covered in section 10.3. Do you know the stuff I was talking about the samples big enough, the data is independent, all that stuff? That's what 10.3 talks about when you go and look at it. So in the first story, a survey is done to estimate the difference in proportions of college students and high school students who smoke cigarettes. Okay. Data on cigarette smoking habits are gathered from randomly selected samples of 500 college and 500 high school. Okay. So here are our choices. A confidence interval should be created or should not be created. What do you think? Here's a surprise for you.
It should not be.
Good. Why?
It doesn't involve comparing.
Yep.
Proportion.
There's no mention in here about proportions. They just said smoking habit. So that could be also, that could be anything, right? How many a day do you smoke? Well, that's not the same thing as a proportion, right? I smoke 10 cigarettes, I smoke 4 cigarettes. There's no proportions being compared here. And that would be better analysed by comparing means. Right. B, 2 new treatments for a serious disease are compared. Each treatment uses 5 patients. I'm stopping right there. Don't need to read the rest. Why am I not going to do a difference there?
It's too little
Sure.
sample size.
Remember the 10 rule? That's what it's sometimes called in textbooks. You got to have at least 10 people who say yes or catch the disease or drink the Coca-Cola, and you need at least 10 people who said, no, I don't have that disease or whatever. The minute they told me it was 5, it's a no. So it's too small. Now, an economist wants to estimate the difference between the mean annual income of college students and the mean annual income of high school students. And that's a trick question. That is a no. Mean college students, mean high school students. Why can't you use a difference in proportions for that story?
They're
Do high
two very
school
different
students
things.
They
have-
are. They're using means. They're not using proportions. I mean, it's kind of an unfair question because your brain is on proportions. But you don't use, this formula doesn't use anything to do with the mean. It's all about how many said yes to something, right? It's all about proportions. Suppose a randomly selected sample of 900 registered voters is surveyed and 45% of them voted for one candidate and the other 55% voted for the second candidate. Why can't we use that set of data to find the difference between the two candidates? So you only ask 900 voters and 45 doesn't really matter what the number is. Certain number of them says, I'm going for the first candidate, and the other said, nope, I'm voting for the other candidate. Why can't you put those two things together and calculate a difference between the two as a proportion? What is wrong with that story? Going to get it? Anybody want to tell me before we get there?
The sample size needs to be larger.
No, 900's pretty good. No problem with that part. Are these
opposite
two?
traits?
Are these two? Yeah, are these two independent of each other? Well, not really. If 40 say yes, won't 60 say no? Right? They're dependent. So you don't want to do that. So, like you were saying, it's a trait one. that's the kind of the intro questions. Now the main bread and butter questions, which are finding confidence intervals, but we're going to do it using SALT. So I have to kind of write down these numbers because I'm very bad at remembering things. A study was done to determine whether there's a relationship between snoring and heart disease. So 81 people out of 1105 snorers had heart disease, while 25 people out of 1375 were not snorers, but they had heart disease. So you try to compare an 81 out of 1105 and a 25 out of 1375. And P1 is going to be the snorers and P2 is going to be the non-snorers. Okay, so I got everything I need. I'm going to hit use SALT. Are you now looking at the SALT screen?
No, I can't see it yet.
Okay, so I'm going to have to do that out and carry on, which is a pain in the butt, but it is what it is. Can you now see the SALT screen?
Yeah.
Okay, so when you are doing the difference in two proportions, you go up here and you make sure you do two sample proportion, right? You got to make sure you pick that one. Now, in this particular question, the snorers were 81 out of 1105. So they count success as snoring and number of trials as how many people it was out of. Now, if you take the non-snorers, there were 25 of them, and this guy here was 1375. And then you click confidence interval, and whatever one they ask, in this case it's 95, so that's great. And then I just hit generate results. And in this list, the important stuff is right here. It says difference in proportions. So P1 take away P2 hat, right? That is 0.055. The standard error is 0.008 and some other stuff. The lower one is 0.038 and the upper one is 0.072. So everything you really want to know is typically here, right in that bunch. So if I now go back here, can you now see use SALT? Back, can you see the question, or we'll have to go in and out? Are you looking at question 3 now, everyone? Oh yeah, good. Right, so the number at the start was 0.038 and the number at the end was 0.072. Now, do you notice that that is what, 3.8% up to 7.2%? You see that? Does that cover 0? No. And aren't all of those positive, right? Every single one of those numbers is positive. So on the basis of that then, since it's positive, does it not mean P1 snorers are bigger than P2 non-snorers? Right? The first thing is bigger than the second because the difference is positive. And can you infer that the population with heart disease differs? Yes, we can. In fact, I can tell you more than that. I can tell you that snorers have a higher heart disease rate than non-snorers because all the numbers were positive. I think that would have been a better choice. Now, that might appear in a kind of medical journal. Doctors, read over things and say, oh, snorers tend to have heart disease. About 3% of them, maybe as much as 4%. somewhere up to 7, and more than non-snorers. So maybe when you're talking to your patient, you might ask them, do you know if you snore? And if they say, yeah, my wife says I snore a lot, then you might say, maybe I should take a little check of your heart just to see. You know, it's not saying that snoring gives you heart attacks. All it's saying is that snoring is like a flag. If somebody is waving it, maybe you should have a little look at what's going on in your heart. Is it maybe useful? Are we comfortable about how I use SALT to put in the data and get that 95% confidence interval? Any questions about that? Are we good? Okay.
Yes.
Right. Let's basically then let's look at some more questions using SALT. So we're going to focus on SALT now for the rest of this part, and then we'll go into the next section. In a study, investigators surveyed individuals by telephone about how often they get tension headaches. One response variable that was measured was whether or not the respondent had experienced an episodic tension type headache in the prior year. I have no idea what that is, but evidently they do. A headache pattern is called episodic if the headache occurs less often than 15 times a month. Otherwise, the headaches were called chronic. Okay. 1,610 women in a certain age group, 655 of them. So that's going to be my P1 data. It's going to be 655 out of 1,610. And then if I read over a little bit further, the other group, it was 994 out of 2,132. So that's going to be my second group. And we're being asked to calculate a confidence interval. Calculate the proportion for this one, the proportion for that one, and then compute that one. And then a 95%. So a lot of stuff going on here. Let's just use SALT to do it all for us then. Right. So two sample proportion. The first variable was 655 out of 1610. The second one was 994 out of 2,132. It was another 95%, and I'll generate the results. Now, they asked a lot of other numbers. So, for instance, they asked you for the proportion for P1. That's this number here, the 0.406. They want the proportion for P2, which is that number. They want the proportion for the difference. That's that number. I don't know if they wanted the standard error, but if they did, it would be that number. And lastly, they want to know the confidence interval, and it's these is the upper and the lower. Do you see that all the numbers that he asked there were in this table? Most of the time, they're just interested in these numbers. But in this particular question, they wanted that guy and that guy as well. So for instance, if I wanted to put in the difference, the difference would be in this question, negative 0.059. And they want 4 decimal places, so it's going to be 954. And they wanted the confidence interval, and that had a lower value of negative 0.0914. And on the other side, it had negative 0.0274. So those numbers that I'm getting came from salt. And then they kind of finish with interpret what this means. So let's look at that. Aren't these two numbers, the start and the finish, all negative? So doesn't that mean that P1 is less than P2? And P1 is 18 to 29 years old, have less headaches than 30 to 39-year-olds. So you just go through this sentence and you find the ones that do that. I guess if I was going to put an explanation of why do 18 to 29-year-olds have less headaches than 30 to 39 years old, is that 30 to 39-year-olds probably have kids. And kids will give you headaches and stress and worry and make your hair fall out and all sorts of things. Have I put you off having kids, those who are in that place? Okay. I was joking there. Kids are lovely. Our family anyway, we love kids. We come from huge families, so yeah. Right. Here is your data. It's put together a little bit differently, but everything you need to know is here. Can you see that is going to be the yeses, and that's going to be the total number asked, and that's going to be the yeses, and that's going to be the total number asked. And we just need to know who P1 is. So P1 is going to be the year 2000, and P2 is going to be that one. Now, if I had time, I would go into salt. I would put this guy, that guy, then in P2, this guy and that guy. And then I could write down what the standard error was and write down what the 90% confidence interval. Can we skip by that? Do you feel you're comfortable about how that process would work? Do you want to see that, or can we skip by that? Your choice, guys.
We can skip it.
Okay, good. Basically, there's just a whole load of different versions of the same pieces of information. So I don't know. I want to just do one more because we're running short of time. Let's do this one because it's a little bit different. So a sample of college students was asked whether they would return money if they found a wallet. Of the 93 women, 87 said yes. So P1 is going to be women, and it's going to be 87 out of 93. And P2 is going to be the men, and 48 out of 75 said yes. And we are interested in the P1 takeaway P2 hat, and we are going to be looking for, yet again, because they have no imagination, a 95% confidence interval. Okay, so I've written down the numbers I want, and I'm going to click on this guy, and I'm going to bring this fellow over. Make sure you can see it. And for the women, it was 87 out of 93 would give back the money. 48 out of 75. Confidence interval 95, generate the results. And the lower limit 0.176 and upper limit 0.415. So I should be able to take that and plug it in here. So it's going to be 0.176 to 0.415. Okay. What about these two guys? Well, these two guys are not even differences. These are single proportion answers. So they just want us to find what is the interval just for women, not the difference. This is the interval for the difference between men and women, but what it is just for women. So if I click on salt and I go here, what you do for a single one is you hit one sample proportion like yesterday. And for the women, you type in 87. And for the men, you type in 93. And it's a 95 confidence interval. And the answer is somewhere between 0.886 to 0.986. So here it's going to be 0.886 and all the way to 0.986. And then you do the same thing for the men. What's striking to me is, look how large the interval is for women. Somewhere between 89 and 99% of women would give back the money if they found it in the wallet. That's a huge number. But why is the difference so small? Why is the difference only 18 to 41%? What the heck is going on there?
It was a larger sample.
Not in this case. I don't think, I know what you're thinking, but no, I don't think that's the main reason.
You're doing women to men?
Yeah, and because you're doing the difference between them, couldn't both groups be really big? If both groups are really big, wouldn't the difference be quite small? You know, if the women were 90 and the men were 80, wouldn't the difference only be 10? Now, if the women were 90 and the men were 20, wouldn't the difference be 70? So what that interval is telling me is, because it's positive, women are more honest than men, right? The women number is bigger than the men. There's clear evidence for that. And it's at least 17% more honest than men. At least that much, probably better. And that's the end of, unless you have questions, of course, the difference between two proportions and confidence intervals. Any questions about what we've just done? Are we good to move on to the next topic? If anybody has a question, now's your chance. Okay, I'll take that as a good sign. And I'll close off as all these windows. And we'll now move to our next section. And that is going to be section chapter 11A. And chapter 11A and 11B, but we're only going to do 11A today, deals with estimating the value of a single meal, the value of a single meal. Right. So let's show you what that looks like. It's very close to estimating, right, finding a confidence interval for a single proportion. Now, if it was a single proportion, p hat, plus or minus whatever particular magic number you're looking for instance, 1.645 times the standard error of p hat. That's how you would get a 90% confidence interval of a single proportion. Now, if you want to find a 90% confidence interval of a single mean, the formula looks like this: X bar plus or minus. This is where it gets a bit sneaky. It might be 1.645 times the standard error of X bar. Now, the reason I'm saying it might be that, but it's very rarely that, is that this number isn't fixed. When it was proportions, if you want a 90%, it's always 1.645, right? Never changes. Doesn't matter if it's 2 million people or 22 people, it's still that number. But when you are doing means of data, this number changes. In general, this number is given a fancy name. It's called the t-score. In this case, this is the 90% confidence interval, t-score. Now you can actually find that number by using a table that I have put in Canvas, or you can find that number by simply just using SOL. So SOL is going to get used a lot more than we did with the proportions. But there are some things that we can still do by hand, so I will do those. If you want to find the standard error of a single mean, its formula is typically S over the square root of n. So it's not a really ugly formula, right? It's pretty easy to calculate. Or it might be, but that's quite rare, it might be sigma over the square root of n. Does anybody remember what the Greek letter sigma is?
Standard deviation.
Yeah. And not only is it just the standard deviation, which it is, it's the population standard deviation. And we use that value sigma, and it is a parameter, right? Any number that comes from a population is called a parameter. So the standard deviation of the population is called sigma. Do you know what little s, or sometimes it's capital S, depends on the textbook. Do you know what S represents?
Isn't it the standard deviation of a sample?
Yep. I'll just say it's SD because I don't want to have to write standard deviation. And that is called a statistic, because a statistic comes from a sample, right? And a parameter comes from a population. So this is a statistic. And this is a parameter. Almost always you're going to be using that. It's very, very rare that you know sigma. But if you get lucky and they tell you sigma, well, that's nice. But don't expect to see it, really. Theoretically, the only way you could know sigma is if you did a census, in which case, why you bother in getting confidence intervals? Because you already know. Okay, so let's do a little story, at least as far as we can go, and show you how you calculate a confidence interval. Let's suppose that I found 200 adult Americans, and I found that their average weight was 203 pounds. And I would like to use this nice random sample to do the average weight of a typical adult American. And I'm going to do a 90% confidence interval. And so it's going to be X bar plus or minus the magic score for 0.90 times the standard error of X bar. Now X bar is 203. That magic number, can't tell you what it is yet, but I will. And this is going to be S over the square root of n, right? Now that guy there can come from salt. That guy there can come from tables of values, right? Can come from all sorts of different places. I'm going to see if I can, you can't see what I'm doing, but I will show you this later. So I'm just busily typing some stuff in here. And the number that I got, this magic number for T, is 1.65. And I'll be a little bit more accurate. It's 1.653. Right, so do you notice that it wasn't quite 1.645, but it's darn close to it, right? And right now it's magic. I'm just telling you that's what this number is. Later on, I'll show you how to find it. So it's going to be 203 plus or minus 1.653 times, oh, I need a story. I forgot to tell you that the standard deviation of my sample was 12. So it's going to be 12 over the square root of 200. So you've now got 203 plus or minus all of that. So 1.653 times 12 divided by the square root of 200. And the answer I get is 1.4, oh, let's say it's two decimal places, right? 1.40. And our interval then, if you take this away from it, you get 201.6 and 204.4. And there you go.
Professor, how did you get the 12? Was that the amount of people with that average weight?
Now that 12 is the standard deviation of those 200 people. So their average was 203 and their standard deviation was 12. That was just a number that you are given in the question. You know, it could have been 22, it could have been 40. You're just told what it is.
Okay, thank you.
So when you look at this interval, how can we interpret this? Well, I can interpret this a couple of ways. A little bit differently from the proportion one, right? But I can interpret it. Would you agree that all these numbers, right, are bigger than 200? Would you agree every single number?
Yes.
Yeah. So I would say that this is evidence to prove that the average American adult is over 200 pounds in weight. Does that make sense? If all the numbers are bigger than 200, that's a reasonable assumption. Would you agree that all of these numbers are less than 205 pounds? Couldn't I also then interpret this interval as the average American weighs less than 205 pounds? I could just say the average American weighs somewhere between 201.6 and 204.4. There is a third way of telling you what that interval is giving me. It gives you a kind of ballpark figure, doesn't it, of what the typical adult American might weigh. Agreed? Now, we are making assumptions just like we did in proportions. The first assumption is that the sample is big enough. Now, that's a bit tricky. When it was proportions, don't you just do the NP, N1 minus P, the 10 rule, right? The number of people who said yes and the number of people said no, they need at least 10 of each, right? So what is a big enough sample? That's like how long is a piece of string? It really depends on who you ask in the statistics world. But there is a kind of vague general consensus that you need to be at least 30 people in your sample to do anything. Would you agree it would be a bad idea for me just to find 3 Americans and find their average weight and use that to predict all American adults? Would you agree 3 is stupid, right? It's too tiny, right? You might not even like 30, right? But at least it's a workable number, right? Would you also agree that the bigger it is, the more accurate your answer is going to be, right? So if I asked 30,000 Americans, I'd get a really good interval. In fact, wouldn't I get a really small interval as well as an accurate interval, which is really good news. Second one, is that it's a fair and representative sample. Right, I'm assuming that the 200 people I asked were a random sample of American adults. Suppose I was lazy and I just went to a bodybuilding club and got the weight of all those people. Would you agree that's probably not a fair and representative sample of the population? Now I'm going to be sexist here. Suppose I only asked 200 men. Do you think that would be a fair representation of all American adults? No. What's the sexist part? Maybe it's not so bad. Women do tend to be lighter than men. Would you agree? In general. That's just the way things are. So if you were doing a sample, shouldn't you hopefully get roughly about the same number of young and old, males and females, bodybuilders and couch potatoes and joggers and everything else, right? A good sample. Right? Third one really doesn't come in too much, but it can be. Independence really only comes in when you're talking about the difference of 2 populations. So suppose I wanted to compare the average weight of an American against the average weight of a Scotsman, right? And those 2 populations have to be separate, right? It's not a good idea if your 2 populations share people, right? Or at least have some kind of connection that would distort your data. And that one is probably not ever going to be an issue with the kind of questions that you're dealing with. But you have to be careful that if you collect data, that your data, the 2 populations are independent of each other, right? They're not connected in any way, because it causes problems if they are. Are we good about, apart from where this magic number came from, how you would collect how you would create a 90, a 95 or a 99% confidence interval for a mean? Feel good about that? Okay, so I'm now going to show you how we would do that. Using SALT. So fingers crossed, I did all my calculations correctly. I'm now going to try and share a SALT screen. You're looking at the SALT screen? Okay, so we're going to go and oh, sorry, wrong SALT screen. Hold on a second, I'll find the right one. Ah. Here we go. Are you looking at question 1, use SALT? Is that good? I think I'm on the wrong one. Can I apologize? I am. That's tomorrow. Right. Du- 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 du. Oh, shooting space. Of course, 11A is the intro and 11B is find the intervals, but that's fine. Let me, can I find one? Okay. Right. In these questions here, they are asking you to calculate the standard error, right? Which you can do by hand. This one here and this one here is going to find the magic t-score. This one here is finding standard error. Okay, so hold that thought until tomorrow and let's just answer these questions, which are from the top then. Suppose you're told that the mean IQ for children is 105.3. Explain what additional information that you would need in order to know if this is a statistic or if it's a parameter. And for some reason, we've got all the answers as well. Just not good. Okay. I know that the average, right, is 105.3. Is it a statistic or a parameter? What would I need to also know? Well, you need to know that. If I know everybody in the school's average IQ is 105.3 and my population is just children at this school, haven't I already found the answer? It's a parameter, right? It's a population value. Now, in these questions, we're being asked to find the standard error. So there's the standard deviation and there's the number. So in here, you would do 14 divided by the square root of 100. And whatever that comes to, I think I can figure out something to do here. I have got an idea. Let's do it the way you would see it. Right. When I click on this guy here, it's asking me to enter a number. And so I said 18 divided by the square root of 100. And the answer to that is 1.8. And then I should be able to submit the answer. Am I good or am I good? So all you're doing here is the preamble, right? You're not actually in this section going to calculate any intervals, right? You're just going to find the standard error or whatever it is they're asking you. So can you imagine in this one, they're asking you for it. So it's what, 63 divided by 49. Which happens to be a nice number, 9. And oh, this one came out of the blue. Wasn't expecting that one. So I'm going to leave that for a second and show you what it is. Slightly out of order, but since it's here, I want to cover it. If you have a single sample, N is the population and S is the standard deviation, then the standard error is S over square root N, right? That's what we did. If, however, you are doing the difference between 2, the formula takes on a rather ugly look. So the standard error for the difference between two population means is this one. So in that question, they made life very easy because the S1 and the S2 are both 48. And the N1 and the N2 are both 288. There is no reason in the world why these should be the same or these should be the same, but they've made them the same. So the formula for calculating the standard error for the difference is this fella. So it's the square root of 48 squared divided by 288 plus 48 squared divided by 288. And the answer is a very nice 4. So that's what you do when they sneak that one up on you. Okay, so that guy was 4. And let's do a submit answer. There. Right. Now, in these questions here, they tell you the mean, they tell you the standard deviation, and they tell you the number. Right? But all you're being asked to find is the standard error. So it doesn't matter what that number is. Do you notice that the standard error doesn't use the X bar value? So if I was doing this question, wouldn't it just be 1 over the square root of 28? Does that make sense? And for this one, it would be 5 over the square root of 103. Right. Now, remember those magic t-scores that I got? And I said, look, I'm just going to get it and I'll show you later where it came from. Let's show you where it came from. Find the magic t-score, right? When the degrees of freedom are 15 and you want it for a 95% confidence interval, right? Now, first thing, degrees of freedom. It's not the same number as the sample size. Degrees of freedom is 1 less than the sample size. So if there's 80 people in your sample, degrees of freedom are 79, right? So you just remember that little thing. But in this case, they're telling me the numbers, so that's great. 15 and 95. Let's show you what you do then. Click on the salt. Oh. Can you see the salt? Right. Now, click on this guy and hit T distribution. The degrees of freedom, I believe, were 19. I'm going to shrink this down a little bit so I can see the whole thing. Right, now, click the between button. Right, and go down here at the bottom. And if you want a 95%, put in 0.95. And the t-score you're looking for is 2.093. Right, suppose you want a 90%, right? The magic t-score for a 90%. Put 90% there. Can you see that the magic t-score will now be that guy? If you wanted 99%, it's now that guy. Are we comfortable about how you find the magic t-score? You put in degrees of freedom, you hit the between, and not here, you don't put anything here, that'll get done by the computer. You put in here what the confidence interval you're looking for, a 90, 0.9, a 99, 0.99. And once you click out of it, you'll see a plus and a minus number here. We use the plus value, that guy. And that would be the fellow that goes there. Oops, well, that won't go there because that's not what I copied. Let's go back. That's a 95 we're looking for, right? So I'll change that to 95. Okay, the number I'm looking for is this one. 2.093. Fingers crossed. Go. Oh, I just saw a mistake. That's my mistake.
I think it just wants 2 decimal places.
Yeah.
Oh, is the DF wrong at all? It's 15.
What else might be wrong? Oh, degrees of freedom are 15.
I think we said 19 as the
I
statistic.
said 19. So I'll put in the 15. And that changes my number. So I answered a different question. Wasn't my question, but it was a different question. I want to try this out.
It's the
Okay.
decimal places.
Yeah, it's I set it up to be generous about rounding off. So you see it's even accepting it, even although I put 4 in. Before I fixed that, if you had put in 3 instead of 2, it would have said you were wrong. But it's a good idea to answer what's been asked, isn't it? So I should really do that. Here's a whole bunch of the same thing. You can find a 99 with 17 or a 90 with 81, right? Now, notice one little difference. I'm writing this down. I'm going to do C, 81 and a 90%er, right? N, the data is 81, 90%. So T distribution, we're good. And this is a mistake. It shouldn't be 81. What are the degrees of freedom? The sample is 81, but how many, what's the number for the degrees of freedom?
Isn't it n-1?
Yeah, so it should have been 80. Now, do you see that? That would be an easy mistake because you see a number and you use it. Now, we're going to be going down here and we're going to do the between again. And it's going to be 90. And the magic number is going to be this fella. 1.6641. And what do they want? 2 decimal places. Now, we're comfortable about how to get the magic t-scores now? Here's some more standard error questions. To get the standard error, isn't it 2.4 divided by 99? So just typing in 2.4 divided by, it won't understand this answer. I'm just putting it in, you know, that's what your calculation, if I could hit the right keys, that's what your calculation would look like. The others are pretty similar. Okay, check my time. Okay, now this one I'm going to do in 2 parts. The first part is pretty standard. The standard deviation is going to be, the standard error, I should say, is going to be 3 over the square root of 49. So, on my calculator, round off the answer to just 2 decimal places. So that's 0.43 I make it. Now, write 1 or 2 sentences to interpret this value, round off the answer to 2 decimal places. Over all possible samples of size 49, the average difference between the sample mean and the population mean is about 0.43. What on earth did the sentence mean? Because I told you the answer. If you take any distribution and you know it's standard error, isn't the standard error just a fancy name for the standard deviation of the sampling distribution? So if you go one standard deviation away from the mean, isn't that roughly where a big chunk of the data is going to be? So in those questions, you're really just repeating whatever the standard error is, right? So if it talks about a sample mean of the population is about this far away, that's probably correct. Now, I'm going to move away from that for a few moments, and we'll talk about, in more general terms, confidence intervals and their connection to sample sizes. Suppose I have a sample of 100, right? And that the standard deviation is 10. I'm picking numbers to be easy to calculate. The standard error of the mean would be 10 over the square root of 100, which is 1. Now, if you can imagine what that might look like, well, I'm saying 1, but who knows what that number is, right? 1, 1, 1. Minus 1, minus 1, minus 1. Now, what happens to the size of that interval? So can we imagine that that's what the interval looks like from start to finish? And let's suppose that's what a 90% confidence interval will look like. What would happen if I did a sample size of 10,000? Then if the only thing that changed, right, was the size of the sample, can you see that the standard error is much smaller? See, from there to there is only going to be 0.1. And so the interval that you would get would be much smaller. Now, isn't that exactly the same property that is true for proportions? For the same 90% confidence interval, right? So imagine it was just a 90% confidence interval. If you have a sample size of 100, 10,000, or 1,000,000. That might be the interval. That's the confidence interval. It looks like that. Won't it be smaller with 10,000? And if you did 1,000,000 people, wouldn't it be almost the same number, right? 8.11 to 8.12, right? A very, very narrow margin, right? So confidence intervals get smaller when sample sizes get bigger. Does that seem logically sensible? That the more people you ask, the more accurate your answer is, and so the narrower your interval is going to end up being, because you're really, really sure that it's somewhere in a very tight area. Now, if this is a 90% confidence interval for a sample size of 100, what would a 95 and a 99 look like if you kept the sample size the same, but you increased the confidence interval? So you did a 95 and then a 99. Would the 95 be bigger than that, a bigger interval, or smaller than that? This is a 90. What would a 95 look like?
Bigger.
Bigger. Because if you want to be 95% sure, don't you have to have a bigger interval to be more sure? And if you want to be 99, don't you have to have even a bigger interval? So as the confidence interval increases, doesn't the interval size increase? As the sample size increases, doesn't the interval size decrease? Do you see that there's a different relationship here? As one gets bigger, the other gets smaller. That's this one. As one gets bigger, the other one gets bigger. If you're into physics, these are called direct and inverse proportions. I don't know if you've done anything in physics. You ever heard inverse proportion when you talk about things? Okay. Forget that phrase, doesn't matter, right? But that's what they're called. Okay, so now that we've kind of did that little side issue, let's return for the last of these questions and see what we get. Suppose a randomly selected sample 169 gave you this guy and 121 give you that guy. Calculate, oh, that's a standard error question, right? I've already told you the formula for that. Remember the S1 squared over N1 squared? So that's not the question. Right, this is the question. Suppose you increase a confidence from 90 to 95. What do you think happens to the magic t-score? Because if you go from 90 to 95, doesn't the interval get bigger? Now, all the numbers stay put except one number. The only number that changes is the magic t, right? The t star. So what would happen if you went from 90 to 95? Would they get increase, decrease, or doesn't change? What do you think would happen if you went from a 90 to a 95% confidence interval?
The T number increases.
Correct. Suppose the sample size increases. So you keep it at 90%, but instead of using 100 people, you use 100 million people. Well, if that's what 100 people looks like, wouldn't 100 million people look like that? Right? Now, if the interval gets smaller, what happens to the t-value then?
It decreases.
Right. Have you noticed that the t-value does the same thing that the interval does? Right. If an interval gets bigger, it's because the t-score got bigger. That's what made it bigger, right? If an interval gets smaller, it's because the t-score got smaller, right? That's kind of what, provided everything else stays put, right? If you don't change anything else except that one thing. Okay, this is a sneaky one. The degrees of freedom increases. So you go from a degree of freedom in 99 to a degree of freedom in 999. Now you have to think this one through. What is the net effect on T star? Give you a clue. Do you know if degrees of freedom are increasing? Isn't that just a disguised way of saying that the sample's getting bigger? And when the sample gets bigger, what happens to the confidence interval? It gets smaller. And if a confidence interval gets smaller, doesn't the T do the same thing? Does that make sense? So you see some of these ones are not clear. You have to kind of, it's like this leads to that, leads to that. Like it's like 3-jump logic. Okay. I haven't even talked about this one. What happens if the degrees of freedom are essentially infinite, as big as you like, right? Extremely big. That's a thinker. I haven't mentioned it. Well, not directly. Remember I mentioned right at the start the 1.964. And the 1.964 is the normal distribution guy. So the T distribution just turns into the normal distribution. Because essentially, if you ask everybody, don't you know the population now? It's a normal distribution. I'll let